So, B peak has got some drawbacks as well, like computation of B peak time is dependent on the size and value of the test vectors. So, the best primary input change. So, when this will be done, so as I have said that it is not there is no straightforward way to tell it. So, it is very much circuit dependent and of course, the pattern dependent as well. So, maybe for the most difficult part is that for different patterns the best input change time may be different. So, as a result it may be difficult to come up with a very some fixed input change time for all the test patterns. So, that creates a difficulty and this may result in high computation time limiting applicability of B peak to reasonably large circuit. So, that I have seen told that okay, this will take lot of time to find out it, but definitely it can improves this power significantly. So, and since it is an one time effort for a given test pattern set, so it may be the case that we go for this. And test set independent strategies are preferred, like we should have multiple scan chains. So, one possibly, so if multiple scan chains are there, then this individual scan chains are of shorter length. So, as a result this number of shift cycles will be less in this case. So, naturally we can have this multiple scan chain based strategy and B peak can be computed there because the number of shift cycles are less. Another class of techniques by which we can reduce this scan power are known as scan chain transformation technique. So, one possibility is the scan flip flop reordering that we have already seen, like that scan cell reordering basically. So, we can change the scan, we can do scan flip flop reordering. Then we can traditionally these scan chains are made up of D flip flop, where this Q output of previous flip flop is connected to the D input of the next flip flop. But what about the Q bar input? So, Q bar input can also be used. So, if we do that, maybe we can reduce some transitions. Sometimes we can change the type of flip flop that we are going to use in the scan chain. Okay. So, instead of normally we are suggesting D flip flop, but we can go for some other types of flip flops as well, like say T flip flop, etc. Sometimes we modify the scan chain by putting some additional gates into the circuit, and most of the time an XOR gate is put, because XOR gate has the possibility of complementing the input, and that way XOR gates are used in many cases, and we have got multiple scan chain based design. So, that is also there in many situations. So, we will start with an example when we are using both the outputs of a of flip flops. So, this is the first the left side. So, this is the standard scan chain where the D input of a flip flop is connected from the Q output of the previous flip flop, so in forming the scan chain. So, if the final pattern is 0 1 1 1, so this is what we want to achieve, then we have to do the shifting like this, assuming that initially the flip flops are all 0, then this 1 has to be shifted, then again this one, then again this one, then this 0, as a result finally you get this thing. So, number of transitions. So, here I have got 1 transition, 2 transition, 3 transition, 4 transitions. On the other hand, if suppose for the second flip flop the D input is connected from the Q bar output of the previous flip flop. Now, here in this case since this Q output was 0, Q bar was 1. So, when we are shifting, we are applying a shift pulse, then this 1 that we have at this point gets shifted to the to this flip flop. As a result, this becomes 1. Okay. So, this way the pattern that you need to shift will be different, the input that we have to apply here will be different. For example, in this case we have to always keep it at 0. Okay. So, that finally we get 0 1 1 1 as the content of the scan chain. Okay. But number of transition gets reduced. Okay. The first cell does not see any transition, this cell sees 1 transition, 1 transition and 1 transition, total 3 transitions can be obtained. So, this way by modifying some of the D cell some of the flip flops from Q to Q bar connection, so we can go for scan transition reduction. So, this may be one possibility of reducing the scan transition. Another possibility is by using a mix of flip flops. So, D type and T type flip flops. So, in fact, traditionally we are using D flip flop for this scan chain formation, but we know that there are many other types of flip flop and T flip flop is one such thing. So, So, for normal operation of the circuit, so the structure is modified like this. So, for the normal operation of the circuit, so this shift pulse, so this shift is the scan enable or shift, so that is equal to 0. So, the normal input goes to this multiplexer, it comes to this D flip flop. So, there is no problem, but for the scan mode, so this input will come through this XOR gate. So, what we are doing, this Q output is XORed with the next input. So, that this becomes this entire structure XOR followed by D, it behaves like a T flip flop. So, it is the flip flop is not changed. So, flip flop type is not changed. So, for the normal circuit operation there is no problem, that still remains as a D flip flop, but in the test mode these flip flops are converted to T flip flop. Now, it may be the case that this D flip flop, this it may be the case that modifying all D flip flops to T may not be beneficial, maybe for the best result we need to modify only some of them. Of course, there is a catch here, because some of the flip flops are now modified to T flip flop. So, the response part will also change, because when this an input is applied to T flip flop, it behaves differently compared to a D flip flop. So, the whatever response the ATPG has told us, okay, these are the responses. So, that will not be valid. So, we have to recompute them based on the scan chain architecture. So, again another fault simulation has to be done. So, those are there, but if it is beneficial, we can modify some of the D flip flops to T flip flops. So, this is a typical example, like say if I have got all the flip flops as D flip flops, then to get this final pattern 0 1 0 1 onto the scan chain, we have to apply shift in the bits like this, and that creates a total of 9 transitions. On the other hand, suppose we modify these 3 flip flops to T, from D they are modified to T. So, what will happen? So, this will be doing transitions, the transitions will come like this, and if you compute the number of transitions, so here there are 6 transitions. So, number of transitions are less. So, this gives rise to a better way of getting the power reduction. So, you can get less power because the transitions are less. So, circuit is also expected to generate less transition. Also, another popular strategy is to include this some XOR gate into the scan chain itself. Like you see, the normal case what is happening is that these D inputs are feeding these successive stages, and it is going like this, the scan chain is going like this. Now, if we put an XOR gate, so that this input that we feed to this stage is a sum of these two. Okay. So, the sum of this input and this input. So, in normal matrix, so test stimulus matrix, so it is like this. So, whatever be the input, so that will get modified there is, but in this case, so this matrix if you multiply by the given test stimulus, so you can find out what is the new stimulus that you should apply for getting the particular pattern onto the set. Now, this can reduce the transitions, though it is not very obvious that whether it will always reduce transitions or not, but this can happen. Like say it is original test pattern set may have 14 transitions. So, when you are post multiplying it by this, so we are getting 10 transitions. Of course, this calculation is this is not weighted transition. So, this is just assuming that these patterns will be applied directly to the test set, to the circuit. Okay. So, there are some 10 transitions in this case. Like here I have got one transition, here I have got so this way actually, this is one transition, this is one transition, this is another, this is another. So, that way if the patterns are going sequentially through this scan chain, so it creates 10 transitions. However, this is these are not weighted transitions. Okay, this calculation 14 or 10, but the work that is reported in the literature, it is reported like this. So, of course, this weighted transition values will be different. So, that needs to be computed. We can also use multiple scan chain. Okay. So, multiple scan chain, we have the concept we have already seen. So, because a single scan chain, since there are a large number of scan flip flops, so this may be the scan chain may be large. So, it will require large number of scan shifts. So, we can take help of this multiple scan chains to reduce this. So, the test area will be reduced because I do not need to have these long interconnects connecting all these scan cells, and this test data volume overhead is also reduced in some cases, because we can do because of this multiple scan chain. So, we can form test slices, and many of these compression mechanism like Huffman code and that. So, they rely on this scan slice. Okay. So, that way we can have this test volume can be reduced by doing the compression. So, test application time is can also get improved. So, there is no penalty, but rather it can improve because this shifting can be done faster. Efficiency, performance, they do not affect. However, so extra hardware is required, and that can be specified at logic level and synthesized with the rest of the circuit. So, we need some separate scan control hardware. So, the multiple scan chains are there. So, scan control hardware is there, but of course, we can when doing the synthesis. So, that they with some part of it get merged with the design itself. As a result, this overall area requirement may not be that high, and they are embedded in VLSI design flow, and most of the CAD tools allow it, that we have seen. So, this is a typical structure of multiple scan chains that we have seen here. What is happening is that this scan control block. So, it actually selects one of the scan chain, and then this scan chain data is loaded into it. Now, it can be a broadcast scan or serial scan. So, for broadcast scan, so all these select inputs will be made equal to 1. So, whatever scanning data is coming, that will get loaded to all the scan chain, or it may be a serial one. So, serial one, that will be loaded one after other. First this chain is selected, then this chain is selected, then this chain is selected, etc. And for the scan out purpose, of course, I have to do it serially. So, there this scan this AND gate has to be enabled. As a result, this chain will come, this chain output will come, or this will come, or that will come. So, of course, there are many other components that can be there like scan chain masking and all that. So, that is not shown here. Now, when we are doing this multiple scan chain formation, so we need to partition the scan cells. For doing this partitioning of scan cells into multiple chains. So, we first classify them into compatible, incompatible, and self incompatible and independent. So, these 4 classes. So, compatible S0 and S1 are said to be incompatible as different values are needed at X0 to suppress spurious transitions originating from them. So, this S0 is feeding this AND gate, and S1 is feeding this OR gate. So, if the situation is like this, now if you are having a control to, so that we can mask off this scan cell result going to the circuit. Now, since this is AND and this is OR, so I cannot use a single value of X0 to suppress both the transitions at Z0 and Z1. So, one of them will cannot be suppressed by setting Z0. So, that way this S0 and S1, they are incompatible flip flops. Similarly, S2 and S3 are compatible. S2 and S3 are compatible because by setting this X1 to 0, I can suppress both Z2 and Z3, transition in both Z2 and Z3. Similarly, S4 and S5, they are compatible. So, scan chain that we make, I should make it with the compatible set. So, S0, S2, S3, so they can be made into one cell, one set. S0, S2 and S3, they could be made into one cell chain, and S1, S4 and S5, they can be made another chain. So, we divide it in such a fashion that by setting a single mask, so I can suppress all the transitions that are occurring from that chain. Okay. So, when I have got this S0, S2, S3 into a set, so we can S0, S2 and S3 in a set. So, we can control them by setting X0 and X1 values to a particular values, so that they will not transit. Similarly, this S1, S4 and S5 being in one set. So, I can set this X0 and X2 to some value, so that spurious transitions do not go. So, there is no conflict in the setting of X0, X1 and X2. So, from power minimization point of view, so we can do this type of grouping. Though your scan chain, this interconnect length requirement may require this scan stitching in a different order. Other the self incompatible. So, self incompatible is like this. So, S0 is a self incompatible because any transition for setting for any setting of this X0, the transition proceeds either via T0 or via T1, because X0 is 0 or 1. If it is 0, this Y0 will go to T0, X0 is 1, then it will go to T1. So, that way this S0 becomes an self incompatible. So, it cannot be controlled anyway. So, they can be put into any arbitrary group because they are not compatible with itself. And there are independent cells like S0, S1, S2, S3, they do not have any side inputs for gates T0 and T1. So, naturally I cannot have any control over them. So, it depends explicitly on the values at S0 and S1. So, this S0, S1, S2, S3, they are all independent. Okay. So, primary, so we can add some primary in compute primary inputs to eliminate spurious transitions. So, how can we do this? So, T1 removes the spurious transitions originating at S0 and S1. So, T1, if I can put this T1 to some value, then it can avoid transitions going to Z0. Similarly, S0, S1 and T0 are excluded from the reduced circuit. So, we do not consider this S0, S1 and T1. So, for this spurious reduction, because T1 can take care of this S0 and S1. So, Z0 is modified to a buffer. So, Z0 is just as if this X0, X1 is coming and it is going there, and targeted fault in the reduced circuit is T1 stuck at 1. So, if I can generate this T1 stuck at 1, for that purpose, so this is the I have to set this X0, X1 to such a value, so that I get a 0 at this point, because if I get a 0 at this point, this one this T0 will get suppressed. Okay. So, this T1 should be stuck at 0, stuck at 1. So, that is so a fault generator ATPG can be used for this purpose. So, we have to have these test vectors generated like 0x and x0. So, either of x0 or x1 will be set to 0. So, what the ATPG can help us in telling the setting of this extra inputs, so that this Z0 does not see any transition when S0, S1 they are shifting. So, this way we can go eliminate the spurious transitions from the of scan chain reaching the circuit. There are some clock scheme modification technique. So, this test powers another major source of power consumption is the clock tree. So, clock distribution network. So, that goes to the entire chip, and when it goes to the entire chip, so it affects the almost all the components that we have in the circuit, because almost all parts of the circuit they will require the clock signal. So, when the transitions occur, so due to this long wear of this clock, so it will consume power, plus it will create transition in most of the parts in the circuit. So, we do what we do is that we generate and order test sets, so that some scan chains can have their clocks disabled for portions of the test set. So, the scan chain for which we do not want to apply the shifting process, so we can stop their clock signal. Okay. So, this will the flip flops will not transit, as a result it will reduce test loss. So, if we have got multiple scan chains, then the portions of the circuit that those scan chains which are not shifting the patterns or responses, so we can stop their clock, so that this clock is not there. So, gated clock for scan path and clock tree feeding the scan path. So, this is the gated clock can be used, that is what I was telling. It lowers transitions and minimizes average and peak power, and also the energy consumption. So, this average and peak power minimization, so this will save the circuit from getting damaged, and this energy consumption, the peak power reduction will ensure that it is not crossing the power limit of the circuit the design. So, it will protect the circuit, and this average power minimization. So, this will improve the energy efficiency. Okay. So, battery life will get extended. Another possibility of power reduction is via the test scheduling algorithms. So, we can have a distributed BIST control scheme that can be used, which will schedule the extraction of each BIST component, a BIST element, to keep power reduction, power dissipation under some specified limits. So, if we have got several circuit modules, they are BISTed. Now, I can have a BIST control mechanism by which we do not enable all these BISTs simultaneously. So, they are done in some proper sequence, as a result it will reduce power. So, this will reduce average power, because all of them are not tested simultaneously, but test time will increase. There are several SOC test scheduling algorithms that we will see in later classes. So, for this test power reduction based on test bus partitioning, rectangle packing, simulated annealing, genetic algorithms. So, there are many approaches for that. The schemes that take care of power and precedence as constraints. So, there are several scheduling policies that takes care of this power as a constraint, and also precedence, like which part can be tested after which one. So, there may be some precedence constraint. So, they are also taken care of in the test scheduling algorithms. Power conscious test synthesis. So, what is done is that, so this is the normal flow of any design. So, HDL to RTL to netlist to logic optimization, netlist, layout and layout. So, what is to be done is that in the HDL itself we put the description of the BEAST for if it is a BEASTed design. So, LFSR, MISR, Bilbo, C Bilbo, test controller. So, all these are added into the description of the system itself, and then as the system is getting synthesized, this test hardware part also gets synthesized. So, this addresses testability at higher levels of abstraction during early stage of VLSI design. BEAST hardware, it will is inserted at the RTL level itself, and power dissipation during test application in BEAST data paths need to be accounted for. So, this power estimator, so it will also figure out that when the BEAST part is activated, then what is the power requirement. So, this power dissipation is computed that way. So, existing power constraint test data scheduling approaches are optimistic for BEAST data paths, because test scheduling assumes fixed amount of power dissipation associated with each test, which is not the case for BEAST data paths, unless power dissipation is unless useless power is dissipated in the untested modules, because all the parts are being under BEAST session. So, if all of them are getting power, then maybe at present I am not testing a particular module, but that is also getting power. So, that way there is useless power dissipation. So, we have to do something so that this useless power is reduced. So, this is a typical example. Suppose we are going to test the module M2. Okay. So, this MISR MISR 0 and MISR 1. So, they are actually generating the either the test pattern, or they are analyzing the output of the circuit. So, they need to be activated, and this transitions in MISR 1 is not affecting M2, as inactive register R2 can be selected as its input. So, what we do, this is not MISR 1's result need not come to M2. So, we put this R2 in some value, so that this M2 component does not do see any transition, and this multiplexer is in select mode. So, that is R2 signal is sent to M2. So, MISR 1 though it is connected to M2, so it does not affect this one. So, M1 consumes useless power. So, M1 has to be somehow taken care of. So, M1 useless power dissipation has to be reduced somehow. So, selecting an effective low power testing strategy becomes a challenge. So, there may be several angles from which we need to consider it. For example, the implementation context, like whether the technique is for external testing, scan BEAST, etc. So, depending on that, we may have different policy. For example, for BEAST we have seen that there are number of strategies. For external testing based on ATE, we have seen number of strategies. For scan environment and non-scan environment, so we have got this test vector ordering problem changed. Okay. So, that way we have got this cost function for this power minimization. So, that will get affected. So, this way you see that there are a number of ways by which we can see this this external testing, or this the test environment that creates problem. Second thing is that how do we address this test power minimization, whether we act on test sequence or we act on the test architecture. So, if we are allowed to modify the test architecture, like say this the scan chain modification using mixed DT flip flops, or scan cell reordering, or this putting a mask between the scan chain and the circuit. So, this way if we have some strategies by which we can change this test architecture. So, that is one possibility, and if those things cannot be touched, then we have to work on the test vectors, and there we have got the options like test vector reordering, we have got the option of compression, we have got the option of compaction. So, these are the various avenues that we can try out. Now, as a test engineer, so we would like to have some relaxation in the classical test constraints like fault coverage, test time. So, fault coverage actually nobody will accept a situation where fault coverage gets reduced. So, if some of the test patterns we see that they are consuming lot of power, then possibly we can say that okay, we do not apply those patterns. Okay. So, if we do not apply those patterns, certain faults are not covered. So, fault coverage will get affected, but still it may be acceptable because the power consumption is less. So, we can have this thing, this test time, the test time may change, but this fault coverage normally it is not it is not traded off. Then area overhead from hardware modification must be acceptably low. So, this is another burden put on the test engineer, that whatever modification we are suggesting, the overhead should be low. But if we are allowed to take some more overhead, maybe we can do a better test hardware design, and as a result we can come up with a better power mechanism. Okay. So, this circuit performance must be maintained. So, we need to operate at certain frequency only. So, that frequency cannot be spared. So, we cannot it cannot be traded off. So, if we can test at a lower frequency, then power consumption will be low, but that will affect this delay test and all that. Then effect on the design flow, and hence on the design time must be small enough for the solution to be acceptable. So, this is another pressure, because we do not want to put lot of time on testing, though it takes a good amount of time, but if it is still not sufficient. So, we need more time. So, in the design flow, so if we are allowed to put some more time on testing, then it will be better. And designers must make the clock tree as small as possible or disable clock signals as often as possible. So, this is another desired requirement from the test engineer's viewpoint. So, clock tree if it is small, then this clock skew will not occur. So, delay test and all that, so they will be, they can be done properly, and this power consumption will also be low due to this clock tree. So, that way they should, or they disable clock signals as often as possible. So, if we can disable the clock, then this power consumption will be low. So, that way this test engineer may have some relaxation. So, this classical test constraints, if they are relaxed a bit, then this power consumption during testing can be reduced significantly.